So the title of the talk is Design Patterns of Streaming-Enabled Database Technologies. So I first need to unpack this name. It's a little bit complicated, isn't it? So first, design patterns. So design patterns are a bunch of reusable solutions for some commonly occurring problems. Right? So software engineers notice that, some problems are constantly happening in the field that they are working on, and they decided to come up with some canned solutions that can be repeated over and over again. So whenever they are facing with those problems, they can just open the can, apply it to the problem, and just solve that problem and go to the most interesting part of the problems that they need to solve. So now about the streaming-enabled database technologies. So streaming-enabled database technologies are databases that can integrate deeply with messaging service, like Apache Kafka, like Apache Pulsar, like JMS, or other technologies that you might be familiar with. So these databases can either subscribe to a topic. If you're using Kafka, for example, they can subscribe to a topic. So whenever something is published on that topic, it automatically will be written into the database. So if you want to read that data 10 years after, you can just, go to the database and read it from the database. Or they can publish the data from the database into a topic, right? So you write your data into the database, and then the database automatically publishes it into a stream, so you can use that. And if you put these together, you're gonna end up with something like this: that you publish to a topic, the topic publishes it to a database, and the database publishes it into another topic. So now the question is that why not? Why shouldn't we just use the manual version? You can always do a double write, right? You can instead of using the streaming-enabled database technology, you can just use the manual one, from your event producer or from your writer, right to both the topic and the database, right? And that's a very good question. We're gonna compare these and gonna see that why we are usually using the manual one, but what are the benefits of the streaming-enabled one? So the benefit of the streaming-enabled one is that first one is low coupling, right? So when you are going with this model, your event producer only need to work with Kafka, right? You don't need to know how to work with database. So your code is going to remain much more simpler. And because all of these are independently scalable, you can just scale your application, your database, your messaging service, or whatever, and it's going to work really good. But usually these technologies are slow. Problem is that database technologies, they have to commit the data into disk, and, they have to make sure of the consistency and everything. So they are generally a little bit slower than the messaging services, right? So if you want to do this with a normal database, this is going to take a bit of time till it is available in the consumer. So the benefit of the manual one is that because you are writing at the same time to both of them, it's going to be relatively fast. But it is going to be more complex code base, because now your code base has to work with both of the messaging service and the database. And also you're going to have this problem of inconsistency. You write to the database, but you can't write into the streaming service. You write to the streaming service and you don't have it in the database. So you either have to live with it, or if you are not going to do that, your code base is going to become even more complicated. So yeah, this streaming-enabled technologies are pretty cool and we love them, but the problem is that they are very, very slow. So now let me tell you a little bit about Aerospike. So Aerospike is an efficient database. When I'm saying efficient, think about algorithms. When you're talking about efficiency of an algorithm, you're talking about, optimizing the amount of resources that your algorithm use. We usually try to optimize the number of CPU cycles, which it means that the algorithm is going to be faster when you have a more efficient algorithm. So Aerospike is an efficient database, so it means that it is very, very fast. So it means that we have incredibly low latency. So if you work with something like Cassandra is known as a very fast database. So the latency that you get from Cassandra is less than 10 milliseconds. They call it single-digit millisecond latency. So that's what you get from Cassandra, which is considered to be one of the fastest databases in the market. You're 10 times faster than that. So the latency that you get from Aerospike is less than a millisecond, right? So that's the reason that you need to remember this name. We are highly scalable, like most of the modern databases in the market. We're distributed. You can have data centers across the globe to serve all of your customers across the globe. And we are very cost effective. When I said that we're efficient, efficiency means that we are using fewer resources than the competitors. So we are faster with fewer resources. And then most related to this conversation, we are streaming enabled, right? So we can, those things that I showed you, that you can subscribe to Kafka. So when something is written to the Kafka, it's go to the database, or when you write something into the database, goes to Kafka, we can do that. So now the question is that okay, we have a very, very fast database. If we put that in those diagrams that I showed you, what can we get? So, looking at this diagram, so I'm talking about this. We replace this just generic database, generic streaming enabled database with Aerospike. If we do something like that, we wanna see that what's gonna happen. So first, I need to be a little bit more accurate here. So when I'm saying that, Aerospike can integrate with Kafka, we basically subscribe to that topic. So whenever something is written to the database automatically subscribe to that event, and it ends up in one of the tables of the database. We also have something called filters. So whenever something is written to the database and we want to publish it into another topic, we can filter it. We can say that, publish this one, but don't publish the other one. So using these, we are going to come up with some of those hand solution that I talked about, those design patterns that I talked about. But before that, I want to show you a little bit about the speed that I discussed. I said that you're usually not using these because they're slow, but I did some coding and I came up with some latency numbers, or I should say response time numbers that I want to show you. So from here, basically from the point that the event producer right into Kafka, so it's here, it's including, the number that I'm showing you, it's including the network to the topic. From here to where I can read it from the real-time consumer, it takes 2 milliseconds on 99 percentile. This one, for this topic, I'm using Aiven Kafka cluster that Ben provided me. So these numbers are based on that. So they are doing all right. So they can provide you with 2 millisecond latency. So that's good. But we are more interested about this, right? We want to see that from the time that we are writing into the topic to another consumer can read from the database, how long it would take. And that's 3 milliseconds, right? I told you it's a less than a millisecond latency database. So from here to being able to read it from the database, it's 3 milliseconds. And then if you look at this one, basically going over the network, going to Kafka, going over the network again, getting persisted twice on disk in Aerospike, going through a filter, going over the network, going to another Kafka, going over the network. You get here at 8 millisecond at 75 percentile, 95 percentile is still less than 10 millisecond. And then 99 percentile is 15 millisecond, which if you assume the response time, it is comparable with Cassandra, right? So this whole shebang is kind of the same as Cassandra, right? So that's incredible. So now that we have something like this, we can look at this, at how we can use this structure that we have, how this can enable us to do some more interesting things. So let's talk about these design patterns. So let's start with a simple one. So imagine you have two microservices. They are talking to each other over a topic. So somebody says that we need to audit these messages that are being sent over the network. You don't want to really go here and change the code there or change the code there. So the simple thing that you can do is that you can just add an Aerospike cluster there and subscribe to that, so your data get persisted in the Aerospike cluster. We can make it a little bit more complex with adding a consumer to the database. So imagine that you're going with your car to a shop you buy something, you immediately receive a notification. So the notification is the real-time consumer, right? But you also want to be able to go to your app, right, 10 years from now and look at the money that's spent on 24th of November, 2022, right? So you can still use it as a batch consumer. And this is done automatically. You don't need to do anything extra to get there. We can reverse the order. You want to write to Aerospike, and then you want it to publish into a topic. So consider the situation that you are a hosting company, for example. Somebody purchases a host from you. So it's going to take some time till you bring the host up. So whenever the host is up, all the details of it is up, you write into the database that the order is fulfilled, right? At that point, you want to create a notification to send an email to the customer that, your domain is up. So you can use this pattern. We can make it even more interesting with selected event consumer. Imagine you have an IoT system. You have a bunch of sensors that are just emitting data and you're writing all of them to the database. You don't want for all of these to get a notification, but if the value of a sensor is outside of a range, you want to basically notify somebody, or you want to, trigger a new, procedure. So you can create a filter saying that if that value is outside of that range, I want to write it into a topic so I can modify that. This one is my favorite. It's a multi-events consumer. So imagine you have a broker that is doing lots of purchases from different suppliers, right? So the order, when the order comes in, you have, let's say, 5 different things that you need to handle. So you send requests to 5 different suppliers to get all of the products that you need, right? So first, when the first one come back, you write it to the database, but you don't notify the end user that it is done because the other 4 are still not there. So you wait for all of the suppliers to send you the event that you want, and every time this filter block it from sending a notification to the end user that this one is available. But whenever all of the suppliers fulfill their order, you're going to write into the topic, and the topic is going to be consumable by the consumer. And then, and you can do even more complex things like this. So you can actually use that whole shebang that we discussed. So imagine that it's a betting app. You want to get real-time notification about a team scoring a goal, right? So you want to send the user that the team has scored, but you want to allow them to bet on that event when that event is persisted in the database. So you can do something like that with this. So that was the talk. I have a longer version of this talk that includes some showing the code and things like that. If you're interested, follow us, follow our meetup group, possibly in January sometime. I'm going to have another meetup that is going to be a little bit longer, and I'm going to show you the code, a little bit more detail about these design patterns that discussed and things like that. So thank you very much.
So, I'm Sven Hermans. I'm from Devoteam G-Cloud itself, the host of this event here. And we'll talk about streaming analytics, but more specifically on Google Cloud. So first we'll give a bit of an introduction, then we'll talk about the topic, and we end with an example use case. So who are we? We're actually a Google Cloud Premier Partner. So we are across EMEA, actually across the globe, but more specifically, or most prominent in EMEA. We have more than 400 Google experts. We have been the sales partner of the year of the last 3 years. So the Google has recognized it with several specializations such as data analytics, machine learning, etc. So streaming analytics on Google Clouds. Let's start with some numbers. We've seen that, or what Google projected is actually the growth in enterprise data will be 5 times from 2018 to 2025. That's pretty huge. But if we look at streaming data, we actually have 10 times. So we're going from 5 zettabytes to 50 zettabytes. And zettabytes, and so you have terabytes, you have petabytes, you have exabyte, and then you have zettabyte, right? So it's pretty huge, the amount of data we're processing today. And also the portion of it changes. So here we have maybe 10% of the data processing was streaming in 2018. That becomes 30% in 2025. But what's driving all this growth in the real-time data? So that's just our daily lives have changed and are changing. If you look at the digital devices like next-gen manufacturing, your cars, I mean, how many sensors does your car have today? It's streaming all of that data into the cloud. We have a customer that has sensors on all their manufacturing machines, and then we're streaming it into the cloud to do predictive maintenance, etc. You have digital commerce, all your transactions online. You have all the advertisements, every click, view, impression, all of that is streaming into the clouds. Communications, we used to go sitting in meeting rooms. Today, video is streaming, audio is streaming, text, all for us to be able to talk in real time. And then media consumption, think about Netflix, Spotify, etc. So lots of organizations know that they need to become data-driven. They need to understand their data, analyze their data, work on their roadmap strategically. And for this, you need a good BI tool. You need to have your data in one place that's data-driven, which is very important. But on the other side, you have event-driven. And for event-driven, even having one human in the loop is already too slow, right? Everything needs to be automated, needs to be by machines. You need to be able to immediately recommend a product to someone or select or identify which segment he belongs to. So there the time sensitivity is high. So because event activation has a need for speed. We don't want to analyze fraud. No, we want to prevent fraud. We don't want to analyze traffic. No, we want to avoid sitting in traffic, right? So we need to be fast in analyzing it and in taking action. So those are two very important components to get value out of that data. So why are companies actually struggling with this? So first of all, there are usually a lot of different number of data sources that you need to collect. How can you centralize everything in real time and then analyze and take action? How can you do inelastic and so there's usually inelastic and inflexible data processing. Usually the amount of data changes. For example, one of our customers, the Royal Belgian Football Association, who will win the World Cup, by the way, on a Saturday, they on a Saturday, for example, there are a lot of matches. So our traffic increases times 20 or times 50. It's a huge difference. So how can you scale your processing to the needs? Then the lack of readily available skills. So it's always a struggle how to find the people and then upskill them. And then also the disconnected and disparate tool sets. Usually when there are real-time interactions needed, we see a lot of integrations, custom integrations that are happening, but there's no central way of working or framework that a company is using. So why do enterprises then choose Google Cloud to solve those streaming analytics use cases? On one side, it's serverless architecture, a robust ingestion service, unified batch and stream processing. It allows for a comprehensive set of analysis tools and brings flexibility for the users. So let's dive a bit deeper into those. First of all, serverless data analytics. So if you're using Google Cloud, of course, you can set up your own cluster and you can install anything on it. But it also has its native Google Cloud components, which you don't need to set anything up. There's no setting up a cluster. You don't need to provision a machine. You just create a topic or a table or something. So there's no resource provisioning. You don't need to worry about scaling. You might set some scaling parameters to have it how you like. You don't need to update your software. All of that is taken care of. You can focus on the analytics insights and on the processing, what you want to do with your data. So this is how our usual pipeline looks like, right? First, you want to ingest all your data from all the different data sources into the clouds. You want to do your transformations in real time. And then, of course, you want to analyze it or take action. So the robust ingestion service we're talking about here for in Google is Google Cloud PubSub. So it's a scalable, durable event ingestion and delivery. This slide is actually outdated because it has now 3x3 data replication for up to 31 days, so up to a month. It automatically replicates your data into different Google Cloud regions and within a region in multiple zones, so it's very available and durable. It's a simple publish-subscribe pattern. You create a topic, you send data to it, and a subscriber can get data out of it. Pretty normal. It's global by default. So you go to Google Cloud, you create a topic, and suddenly within 2 clicks, you have a global ingestion service available for you. And of course, it integrates nicely with the entire Google Cloud stack. Then you have Google Cloud Dataflow. So Dataflow is actually just a runner of Apache Beam. And Apache Beam stands for batch and stream. So basically you develop your pipeline into that framework. And then it's able to handle both batch processing and stream processing with exactly the same code. So you don't need to have like a different system of doing an initial dump of a database, for example, and then one for the CDC pipeline. You have it all within one code base. It offers exactly once processing with built-in support for fault-tolerant execution. So, of course, those are solutions that are able to parallelize. If something breaks it, it automatically resolves it. And then all the scaling, etc., is managed automatically. So in Dataflow, the way that you develop your pipelines are in DAGs. So you have operators that are after each other. And what Dataflow does, it scales horizontally based on how much data you have, but it also scales vertically each task separately based on how much compute, etc. it needs. So it is very flexible in giving you exactly the resources what you need, not more, not less, so that you also pay exactly what you need. And then you have the comprehensive set of analytics tools. So I'm only touching a very few services of Google each time. But BigQuery is one of the flagship products. So it's a petabyte scale data warehouse. You can stream your data right in and immediately start querying it. You have even in BigQuery, you have machine learning integrated in it. So you can create machine learning models just with using SQL, which is very convenient. On the other side, of course, if you want to go more custom and you want to develop your own TensorFlow models, etc., there's a whole Vertex AI tool stack, which allows you to write your MLOps pipelines and explore and get value out of your data. And then it also focuses on the flexibility. So you have those Google Cloud components, but it doesn't lock you in. All right. For example, you have Dataflow. It's a runner of Apache Beam. You have PubSub, which has native connectors with Kafka. On BigQuery, you have, BigQuery, for example, it's multi-cloud. So in BigQuery, you actually separate the storage from the compute. So you can even query data from BigQuery that is sitting in AWS S3 or in Azure Data Lake. So it's all very open and flexible to make sure that you can integrate it within your stack. And then this is across many different industries. So I won't go over this entire slide to go into detail, but streaming analytics is necessary in many industries. And I'll touch upon 2 example use cases. One for fraud detection of credit cards, for example, and another for manufacturing. So let's take a look how such a pipeline could look like. So credit card fraud detection, as I already mentioned. So how would that very high level, of course, look like? So let's say that you have your data sources, and those can be, again, spread across the globe. You have cash withdrawals, you have account transfers, payments. You need to get them into the clouds. Like we mentioned before, you use PubSub for that. It's global, serverless. Actually, there's something wrong with those slides, but doesn't really matter. So you get them into PubSub. Then, of course, next step is to get those into Dataflow. In Dataflow, you will do the processing. You might be calling a machine learning model that you trained to detect whether it's actually fraud. Also, fraud is not something that you can detect on a single message, right? You probably want to have a window where you can see multiple transfers after each other, because then you might have, instead of having one very big transfer, which can be detected easily as fraud, you might have 20 within 1 minute that are each very small, or more than that. So you need to be able to window that data, aggregate. You can have sliding windows, you can have lots of different configurations are possible, all in real time. It's even able to handle late data. So let's say that I have a fixed window of 1 minute in which I'm processing my data, but there is one of the producers that had network issues, and suddenly after 5 minutes, they only send it. Then Dataflow is able to take the data back from before and still handle it just like it should be handled. And then you have all the different analytics tools. You have BigQuery or the databases like Bigtable, which is made for low latency, etc. BigQuery is more for analytics, and put BI AI on top of it. Or again, to PubSub to take action for alerting messaging. And so those are only very few components of the entire Google Cloud data ecosystem that exists out there. So we talked about PubSub, we talked about Dataflow, BigQuery, but as you can see there's a whole range of databases, services that can help you to solve your data problems. So let's look at one other use case, which is Gen1. That's a customer of ours in Belgium. So they are part of TVH. And so what they have built with the help of us is an IoT platform. So they have their customers, they have big fleets with manufacturing machines, and they basically provide all the sensors on top of it. And then with those sensors, they're all being collected into the platform. And then they can do their fleet management. They can see, okay, where are all my machines? But they can also do predictive maintenance. Like, okay, this machine here is probably going to break because we trained a machine learning model on top of other previous data where we learned that it will almost break. Or there's also the product engineering team. And what they do is they collect data from all the different Gen1 customers. They anonymize it, but then analyze it to be able to make sure that those products become better and that they have a better understanding of their life cycle. So again, here, pretty similar architecture as we've seen before. The data, because PubSub is on the cloud and basically you can send any data to it, but here there's also the management of all the different IoT devices. For this, you have Google Cloud IoT Core. Now, Google is actually moving IoT Core more into they're actually decommissioning it and counting on their partners to have partner-managed services. So that's maybe not the best example here, but it still exists today. And then you have the processing. They have, there are many things happening on the side, but here this central layer is, what today's talk is about, right? So thank you very much for listening.
Now it's my turn to speak. I probably should have said this earlier, actually. Can you all see the screens at the sides as well, just in case? Good, you're all aware of that. Excellent. Want to make sure? So let's talk about sorting data streams at scale. And this is really about personalizing data safely. So I'm going to give you a quick warning up front, which is there are going to be a lot of puns and terrible jokes in these slides, and they are mostly intentional. I wish they were all intentional, but as I find out, I mostly often stumble into these things. Many practice helps, but this time, we'll see. So let's start with the first thing. This is something called personalization, where this is about how evolution over and over again keeps trying to make crabs. Lots of different creatures evolve into crabs. And this is why I work at Aiven, because eventually I evolved into a crab, and maybe you one day too will. So what Aiven is an open source data platform. We have an ecosystem of various databases, streaming technologies, all of which are Apache 2 licensed or better. So we'll host your Kafka, your Postgres, your Flink, your Redis for you in an open environment where you basically just get the best of what open source has with backup and all the rest to go with it. We don't like lock-in. We don't like cloud. We like to be really cloud agnostic. We'll host you in any cloud you like, pretty much off the go. And that's kind of our shtick. It's open. You can take it. You can run with it. And if you don't like us at the end of it, we'll give you all you need to do to run it somewhere else. So, a bit about me. These days, I kind of work as an open source software sommelier. I'll pair you a Kafka, a Redis, a Postgres, and maybe some cheese to go with it. Because that's kind of what I do in DevRel these days. My job is to show you what is possible, and then hopefully you'll take it away, learn from it, and use it ideally on us, but probably on someone else. And I've worked on everything from MMOs like EVE Online to medical devices for real-time diagnostic detection. I've actually managed to write Haskell code in the last 12 months in production for a client in my previous organization, which was hilarious and involved MQTT as the lucky interface layer, but it was a thing I never thought I'd do. And these days I code in Rust so I can make better crustacean jokes. Yes, this is how far I will go. So let's look at mass personalization, and let's start with kind of like the classic arbiter of all things in business, the Harvard Business Review. They came out about mass personalization and how customization is coming to the masses. But if you think about that, that came out in 1997, right? This is a long while ago, back when Titanic was the movie of the day. The high end of technology, of course, was the N64. And yeah, that's the thing. And the problem then is, as time moves on, you wonder, what is mass personalization today? Is it user profiles like Web 2.0? Is it that federated thing where you can take with you? Is it single sign-on and that one identity, like which, who here has opted up today on their work computers? Who here has probably opted up more than once today on their work computers? And this is the idea of an identity you can take with you. Or is it what Salesforce tell us with the Customer 360? The idea of a single view into what a user in your system actually is, allowing you to help make decisions for them, to aid them on their calls. Classically, this is done with something like a customer service desk, where they know you bought this product, they know you had a problem with that product, and they're going to be able to help you proactively. I'll be honest, if our internet providers could do that, I'd be much happier. But hey, we could all live in hope. So why is this even a problem? Is actually kind of a thing. And really what it comes down to these days is the law. The law is changing. Hands up here who's had to do a cookie rejection banner in the last 2 days. Only 1, 2, 3. That means the rest of you don't change websites very often. Because like GDPR, of course, was the big shock to this industry. Like HIPAA came from healthcare and has been around for years, but GDPR was a game changer. But what's really made it the game changer is it's now become model legislation for about 20 other nations. Now, these are just the ones that had good-looking logos. There's at least another 20 or so out there, which are equally draconian, if not worse, than GDPR, often with actually even harsher things that come out of it. Because whereas GDPR will tend to fine you, some of the ones in South America will just block you from their internet. It's that much of a kind of do it right or get out. And particularly in South Korea, where you literally have data residency, which is it can't leave the border, stop, for certain types of data. So, and this is where it gets harder, is it's only getting faster. As Behrad and Sven alluded to, is real-time is a thing. And this is where like real-time data is maybe like 5% of data today. And in a few years' time, it's going to be about 30% is the kind of prediction. But you have to remember that the data volume will have doubled by then at least twice. So the amount of real-time data has gone up even faster than exponentially. So you start running into this thing where you've got to be able to deal with personalized data in real time and much higher volumes than you previously had to. And you've got to be able to do all this without it falling over at scale. So let's set the scene for an example. It's the age of the fintech app. I'm sure, do all of you have phone banking apps? Right? Or at least online banking apps? And this is just page 1 of the Google Play Store. There are another 5 pages. When I originally took this screenshot, there were 3. There are now 5. I took the screenshot in January. And this is how many fintech apps are coming out these days. And the thing about it is that your users want to get and share updates. By get updates, I mean things like share prices, like Mr. Burns is getting here. And by updates, I mean you might be wanting to sell off all that Bitcoin, which is crashing right now. You might be wanting to worry about your Tesla stocks and other things. But it's also the fact that you also just need to transfer money sometimes, and it needs to happen fast because of, particularly with stocks and trading, you want to win, right? Everyone wants to be, victorious. They don't want to have to be buying something which is an out-of-date price. And users aren't really forgiving. Because, if you buy something with a price which is wrong and gets blocked, that sucks. When you do a balance transfer, it just doesn't go through and you're wondering, but I need to pay my rent. So you do it again and then it goes through twice. That is pretty unacceptable. And I've been in a few situations personally where like a balance transfer has gone through twice rather than once because I didn't see the first time. And this is where users are unforgiving, but governments are worse. So actually, it turns out the biggest fine so far is a single fine of 27 million euros for GDPR. And as I said, GDPR is not the harshest of these legislations. So you're kind of getting to a place now where these things are becoming normalized. And GDPR will fine you even if it's a small breach of like user data in the wrong place. Even if you self-report, it'll just be a lower fine. So these aren't these aren't theoretical fines anymore. This is just the reality we live in. So you've got this thing where, real-time data is going everywhere. It's highly personalized because otherwise it can't do anything useful. That's where all the value is, in that personalization. But it also has to be super secure and also only in the right regions or you're going to lose all your money. So you've got to think about the real-time architecture that powers these apps now. And this is like assembling data on the fly in real time with both updates from the wider world, updates from your own databases, updates from the user themselves. So this obviously ends up with a swarm of microservices, and they are great, except they've got to plug them all together. And this means you end up with a layer. And for that, we turn to PubSub, and I don't mean nautical drinking establishments. Instead, I mean, of course, the publish and subscribe model. The best thing about this is we've already had a whole explanation of it earlier, so I'm not going to go into great detail, but there are plenty of options from RabbitMQ, which shows you never have to go beyond version 0.9 to succeed, to things like MQTT, which is almost IBM from the 90s rather than from the 70s. But it shows that you can still just use tech for a long time and it works. No one really remembers NATs anymore, so I've kind of stopped talking about it. But in general, as you can guess from the name of the meetup, I'm going to talk about Kafka. So, you've got this big application, lots of microservices, and you get this Kafka cluster. You get loose coupling, strong guarantees because it resiliently writes data to disks. And it means all this stuff can be plugged together and there's a nice bit of blast resilience between all these microservices just there. You need the blast resilience, as you can see, because things can just explode. And ideally, the end-to-end latency decreases as services are no longer coupled to each other. As Behrad showed us with looking at Aiven Kafka, it can be really low. I forgot he was going to say that, which is great. So then you go global. Like any app, you can be downloaded anywhere. And that means you've now got lots of Kafkas in lots of places because you want your data to be quite near people, because when you start getting to scale, the speed of light becomes an interesting problem. And if your data is going to go zipping backwards and forwards from North America when your clients are in Sydney, that sucks. So now what you've got is these big fire hoses of data. You've got this immutable data because it's fast. It's traveling around in structured logs, but it could be any data because it's Kafka. Kafka doesn't enforce anything directly. It's going between any number of these heterogeneous different services, which all require different things. And they all got finite bandwidth. And here's the real problem is, this data is going everywhere. You can't be promiscuously shared to be nice and available everywhere because you'll just lose all your money through fines. Or you'll not be allowed to regulate you'll not be allowed to be regulated for a regulated industry. You will not be allowed to launch a healthcare app unless you have a story here. A finance app, you could launch it and then you'd be taken down pretty quickly. So how do you make these things talk safely is the real challenge here. How do you get cross-border data to happen? How do you keep it valuable by keeping it personal when it needs to be? And obviously you don't want more REST APIs. So with REST, you could just query and say, give me this, give me that. But now we've got lots of head of line blocking. We've got things talking and requesting, and you're wasting a ton of bandwidth backwards and forwards with these over APIs that now need to be scaled independently. We don't want that. So this is our challenge. Data's not equal. We can't stop the world. We need to keep it in jurisdiction when we can. And we've got this kind of set theory problem of, I need this much personal data over here, this much analytics data over there, and this much just high-speed data from my original source over here. And I need some combination of it in different places at different times for different users. So what tools are out there? So Apache have, of course, got one called Mirror Maker, which is a specialized way of cloning topics from one Kafka cluster to another. It's often used for data replication between clusters, but mostly for backup because it's not very fine detail. We then have Kafka Connect, which is the canonical way of sucking things out of Kafka, out of databases into Kafka, or dumping it into things. Bit of a blunt force object, very good, but of course, it's just a matter of it doesn't do fine detail. We have NiFi. Who here has heard of NiFi by a show of hands? A couple of people. Who here knew it came from the NSA? One person. So it was open sourced by the NSA, which of course makes it automatically way too interesting. So I may have, been completely sidetracked by that and then read way too much about NiFi about 6 months ago. But What it does is it's a kind of an open source live ETL abstraction type tool. It plugs into any service you like and just pulls data out and spits out in a format you like. Really cool, really flexible, really strange, and has possibly the ugliest user interface you'll ever see in your life. It's worth seeing just so you feel better about Microsoft Excel. I genuinely recommend, just to bring down your expectations of what UX can really look like. And then last but not least, we've got Apache Flink. So Flink exists as kind of like a halfway house between Apache Storm and Apache Spark. Yes, everything is in the Apache project. But what it does is it's a very kind of like big streaming processing network designed around the idea that batches are actually just special cases of streams. It does all the kind of clever checkpointing of data. It's very resilient. It scales very clearly, but also it comes with nice, clean interfaces. So how about we use a bit of all of them? Well, not NiFi, because user interfaces we don't want to deal with. We want to make this all low code. So what we're going to look at is using a bit of Connect, a bit of Mirror Maker, and a bit of Flink. The Flink Squirrel, of course, I didn't give him a mustache. I should have. I only noticed this when I got to it. I thought, I don't have any editing tools, so I didn't want to make that. But it should be the little mirror of universe Flink, the squirrel to go with it. But hey. So let's put this in context. You start with a web presence on your application. You have some, let's say Postgres, because it's the most go-to database. You got some front ends talking to it, and you scale it out with some high availability. Then you say, let's add some more services, some mobile support to your application. So you got some Redis caching, OpenSearch or Elasticsearch for search databases, and now you've got mobile apps coming off the side of this API. That's great. And you often want it in country, because this is the data side. So in one jurisdiction, you can have all these things, and you can make them all talk with Kafka. You can live update indexes in OpenSearch. You can keep your caches hot with Debezium and other tools like this. Great. So you have locally an app that works really well. But when you go global, you want to have more things. So let's say in Singapore. So these are the Aiven logos, which of course are wonderfully confusing, which as for always, design team change about every 3 weeks. But these are this week's poison. So the little bird actually is the Flink icon. I don't know why, but I was told it was a good choice. So what we have here is a setup where there's Apache Kafka linking all of our kind of major databases together. And then we have a Flink instance, which is filtering out anything which should not be there. This is taking out PII data. This is taking out anything that can't leave the region. So we can hit a topic, which can then be used on a mirror maker to go to a central place, or come back in the other direction and enrich it with personal data in the other way. Because Flink is just a big processor which can enrich data, clean data, or anything else in between. And this is where it gets good fun, is because it can both clean and enrich. That means you can have clean data over the wire, but when it comes back in, you can make it valuable again. And of course, it gets fun because you can just keep spooling these per region. And now let's work out what we're going to do in the middle, because we often want centralized analytics. Analytics these days doesn't quite mean what it used to, right? It doesn't mean we look at graphs at the end of the quarter and decide what we're doing next. These days, it means in real time, we've got to make a call on whether we want to update our logistics, our pricing, or anything else. So this is where we come to what I like to call the KFC stack. So this is a bit of a fun, yes, I do tell terrible jokes. You might notice we have 11 products for our 11 secret herbs and spices. Yes, I went deep. And the thing here is that with these kind of tools together, with Kafka, we have streaming data. With Flink, we can denormalize tables on the fly to build up a columnar store to do real-time queries. This actually works really well. We've actually been rolling it out with like IoT clients on the go because you can absorb almost any amount of data in Kafka. With Flink, you can make it rich and interesting, take out the bad records because IoT is not clean, and then put it in something like ClickHouse and you get single digits millisecond queries. Again, a bit like Aerospike, but a different focus. You can't update this data. Instead, you can query it. It's like Aerospike for analytics. And once you have that, you have this kind of big global approach, which is where you have your satellites, each in their region, each safe, each secure, each in its own VPC, and each not leaving a jurisdiction. Then what you have is the ability to have securely shared data over to your central clusters, which is not actually got anything sensitive, which cannot leave the jurisdiction. With gambling data, this is often where you can't have a user's stuff leave a state in America. So when you're actually doing betting data, each state is actually a residency zone. So you cannot leave that state when it comes to person's data. However, the spread for that bet is updated in one central place, probably in Vegas. So the fact of the matter is that bet data needs to go over the wire, needs to be analyzed, need to update the odds, and it needs to go back, but then be re-enriched on the way back. And this is where Flink comes kind of magical, is because it can do both sides. You can enrich on one way and you can clean on the other. So how is this no code, like my little blurb promised? So the key thing here is you can deploy all this on Terraform. right? It's all open source. There are plenty of like proper Streamsy type recipes out there for kubes if you want to do it yourself, or you can do it on us with one-shot Terraform. With Flink, you're using SQL, right? This is out the box, just write SQL. It will work. It will stream process. It will scale because Flink SQL is built to deal with this kind of thing at any scale. Then what you have is schemas. So Kafka ships with a schema registry. We actually have our own fully open source Apache 2 licensed one called Carapace. And the idea here is that with schemas, we can enforce this change. This means that the schemas per topic, like the output topic, is actually enforced. So we say, actually, no, you can't have a field that says person in there. You've got to have these clean fields going over the wire. And the fun bit then is you've enforced this data, you've cleaned it up, you've enforced it, and then it's coming out in more Kafka, in more ClickHouse, in other databases. These are language agnostic. We can use the standard drivers for any of these tools. We have not locked you into any other technologies at this point. We've not locked you to Java, like if you use Spark, or locked you to Python if you use Spark. Yes, I will bash Spark every day. That's just one of those hills I will happily die on. But the key thing here is we want to keep it agnostic. We want to keep it open. We want to keep it flexible. And none of this has given you any kind of restrictions because we need to keep that hot path safe. So the hot path here is what's often referred to as that line the data has to go in to make a decision as fast as possible. Let's say you're dealing with a trading app and an event happens, like you have a very large liquidity event. Someone has just sold half of Facebook. It might happen today, right? Particularly with the current volatility. And that means that you need to make sure that all of your users on your app are alerted to that price change ASAP and have enough access to liquidity, hopefully, particularly for high net worth rollers, that they can then liquidate their positions as fast as possible, as they are probably paying you a lot for that high-speed data. So what happens is that thing needs to go over the wire as fast as possible. It needs to be clean. They need to be able to send back their buy signals, their intents, their sell signals back, and it needs to come back to your central HQ so you can make a decision of where or not to honor a price, or to jack up your margins and make those really, really wide spreads, which is probably going to happen in this high volatility environment we live in. But this is where it has to be hot. The hot path has to be safe, though, because anytime you leak, suddenly the SEC are going to be on you and say, hey, are you the next Bankman-Freud, whatever his name is, with the FTX kind of nonsense, because you're now leaking data left, right, and center? You don't want that, because the fine will eclipse anything you could ever make. So you got to keep it safe. And one last thing is, if you don't try any of this, this is a little challenge we have. It's fully open. It'll work on open source Flink and comes with providers for that. So this is a quick QR code to take you to a fun free credit thing where you get to explore data pipelines with Flink and SQL. This will be sent around again. If you just talk to me afterwards, I'll send you links to it directly. This comes with a credit code and you can just play around with both Flink, Kafka. If you can complete our challenge and send it out either to the email address or tweet it at me, we have a big swag bag for anyone who can find the answer to the challenge. And thank you. And any questions?